We are recording. Go on.
Okay, people. I'm very happy to see you all here in the room and outside the room on our weekly theoretical computer science seminar at the Jagiellonian. Today, I have a very big pleasure to introduce you Wojciech Czerwiński from University of Warsaw, who is a specialist in many things, but in automata theory, especially infinite ones, I believe, right? Right. In infinite states, even. I like that. Even infinitely many states, right? And at some point, he was in some group got a lower bound for the problem he is going to talk today about going on the grid and dimensional grid in a sense, right? That's how I see the result, and it was awarded the best paper award at Stock in some 3 years ago. 3 years ago. 3 years ago, I think, yeah. But except, so he has more than this paper. He is constantly publishing papers on leaks. iCalc has also another paper on Fox, I believe.
Yes, also about this topic.
Also about this topic, right? And on the top of that, very recently he got the ERC grant. Anything else? Let's see.
The title of the grant.
The title of the okay, so that's only soda and pots I noted in your list of papers. Okay, the title of the topic is just reachability problem in vector addition systems on multi-dimensional grids. We will see.
I will show.
We will see. Okay, so the floor is yours.
Thank you very much for a nice introduction. Yes, so I will tell you about vector addition systems, which I abbreviate as VASs. My plan is first to give you basic definitions and some definition of main problem, which I will consider, like the reachability problem. And I will give you some context on research history of this problem. And then I will formulate you like a theorem, which was, let's say, the main point in this recent progress. And then I will jump to techniques. And I would like to, so my main point is to give you intuition about the systems. So I will first show you some stuff with, so yeah, I will talk about this, let's say, automata with many counters, which are vector addition systems. And I will first try to give you intuition that you can implement complicated things in pretty easy automata. And then I will, and this is like old stuff. And then I will try to show you ideas about behind techniques which we developed recently. And that's it. I plan to talk for 90 minutes, so I will not cover everything. I just have prepared more material such that I will not run out of material, but we are relaxed with time. So please ask me questions whenever anything is unclear, and I will be happy to have any interaction. We are not too many, so I think we can allow ourselves for some discussion. Yeah, okay, so that's it as for introduction. So what I will be talking about. So I will let me be about vector addition systems. But actually, I will focus on a bit, on roughly speaking, equivalent, but a bit more robust system. So I will say with states. There is essentially speaking no difference between these two, and I abbreviate this as vector addition systems states. And I also say VAS. And usually, yeah. This is VAS, and this is VAS with states. Okay. So what is this? I will mainly define things via examples, but I hope it's you are all familiar with finite automata, I guess. Yeah? So I will give you an example of a VAS. VAS is essentially speaking automaton with counters. With a bunch of counters, I will give you an example with 3 counters, and these counters have integer values, but necessarily non-negative integer values. This is important. So here you have 2 states, let's say P and Q, and you have 4 transitions. Check. This is some detail. 4 transitions. And we have the following effects. And here is 0, 0. So what does it mean? So for example, we can, if we are in state Q, we can fire this transition and go to state P. And what this means? This means that you don't touch first counter, you don't touch second counter, but the third counter you decrease by 1. Yeah. So you can also think to your current vector, you just add this vector. Yeah, so this is why it's vector addition system. So let's just have a look. Yeah, so what is the semantics? So imagine that you are, let's say in, okay, so these are called states in configuration. So this is an example configuration. State together with counter values. So this I call configuration. So I mean to also be sure about semantics. So what happens if you are in configuration which has 0 on the first counter? You just cannot fire this transition. Yeah, it's not that you just cannot fire it. This is not a random example. This is a famous example from Hopcroft-Pension paper from 1978. And this will be like a beginning, like a first example from a family of interesting examples, which I will show you, which will, roughly speaking, have big reachability sets. So what is a reachability set? If I start from some configuration, I define reachability set from this configuration as a set of all configurations to which you can reach, by some runs from this configuration, by firing a sequence of transitions. And let's analyze. Okay, so let's analyze how this can look here. So let's say we start from some configuration P, K0. So we are here. So what we can do, we can fire this transition many times. What this transition does, it decreases first counter by 1, increases second counter by 1. So you can think it kind of transfers value from first to the second counter intuitively. Yeah? So if you fire this transition k times, I just write 1 arrow, it's k arrows, you will go to P0k and then k. Yeah. So what you can do, you can jump to state Q. And here you can fire this transition. So what this transition does, it decreases second counter and increases first counter by 2. So you can think, so what if you fire this transition k times, you go to Q 2k 0 n. Yes? So you can think that this somehow multiplies. Transfers value back from second to first counter, but somehow multiplies. Of course, this is not really a multiplication. You can call it weak multiplication because you are not forced to fire it exactly 3 times. You may fire it less times. You can fire it 0 times. Yes? But there exists such a run. And then you can jump back. You can jump back to P 2k, 0, and minus 1. Yeah. So this is an example run, but let's go a bit further. So what you can do is you can multiply first counter by 2 for the cost of decreasing the third counter by 1. Observe that this transition is the only transition which touches the third counter in this bus. So if you start from 1, 0, n, you can keep doing this. You can do this. You can go to 2, 0, and minus 1. And after n such runs, you can go to p 2 power n 0, 0. Yeah? And then you can fire, let's say, this transition any number of times. So you can go to p 2 power n minus a, 0 for any a in between 0 and 2 power n. So here you can see that the reachability set contains all these configurations, so at least exponential. But also you can observe that it's actually finite. How to see that it's finite? Well, you only decrease the third counter here. So you start from n, so you can only fire this n times. So after some time in a run, you will not be able to fire this. So you have to stay here, maybe go there and stay here. But here you cannot stay forever because you decrease first counter. Then if you go here you cannot stay forever. So actually, I hope, you see, yeah, that the reachability is finite, and actually it's exponential. Okay, so this was like an introduction, but also I hope you already see some what kind of combinatories you can do here. So what is the main problem which we consider? So this is the reachability problem. So you are given a bus source configuration from which you start, and target configuration which is your target. Yeah, so let's say source S, target T. Two configurations, so states and counter valuations. And question is, let's say bus V. Yeah? Question is, can you reach T from S in V? Okay? Is T reachable from S in V? I hope it's clear. Yeah? So this is the question. And this was a famous question. Yes, I hope this is still a famous question. It was formulated. So maybe one remark. So I'm talking about buses, but there is almost an equivalent model of Petri nets, which I think it's much more known. So I would say this is the same model. There are some tiny details which I would just prefer to work with automata with counters instead of some markings. I think this Petri nets are essentially speaking buses, but obfuscated a bit. But historically they were defined like that. Yes. So you should know this is the same. So this model was defined. So this problem was considered since '70s. And when I first heard this problem, I was thinking, this can't be hard. It can't be hard to solve it. You just have a bunch of counters and reachability problem. And I think that, and maybe you feel the same. But think for 2 days and you should solve it. And this intuition, I think, comes from the following. Yeah, so maybe I will draw it. So the question is for in 2D, yeah, you are here, you have something here. Is there a path here, but you cannot go below, you cannot go outside this quadrant. But if you are allowed to decrease your counters below 0, then this is easy. And I think this if you are allowed to have such paths, if you ask do I have a path in a system which is called an integer path, in which your counters can go below 0? This boils down to counting how many times you have fired some transitions, and when you go to linear systems of linear equations, and then this is empty complete. But the main point, so this is really going traveling in a grid, but the main hardness comes from not from the point that this is traveling in a grid, but that this is traveling in a restricted part of the grid, which makes it, complicated. Okay. But I hope it's okay. It's okay. Yeah. So what's the history? I will just give you a list of, let's say, I will tell a bit about this history. So I think first important result was by Lipton in 76. So that was exponential space hardness of coverability. What is coverability? Coverability is a bit different problem. You are given source and target, but your question is, can you go from source to target or something higher, something bigger? So if here is your source, here is your target, you are asking, can I reach this area? Do I have such a line? Of course, I'm not drawing states here, yes. And you can see that coverability is an easier problem than reachability, because if in your system you have transitions which just decrease counters, for each counter if you have this, then reachability is the same as coverability. I mean, okay, maybe just remember coverability is easier, at least as reachability is at least as hard as coverability. So this implies space hardness of reachability as well. And this was before getting any decidability of reachability. Maybe then, okay, I will write this name. And here you have availability in exponential space. And the idea was, and this is a typical approach for buses, that if you have a path from source to target or above, because this is coverability, then you also have some path run, this is the same thing here, some path from source to target or above, which is not too long, which is of length at most double exponential. So this was the main lemma. If there is a path, then there is a path of length at most double exponential. If you know this, you can search in exponential space for such a path. So that was the main thing. Maybe then I will tell you then in 81, decidability of reachability. Yes, so that's 5 years after this. But the algorithm, the Meyer proved this decidability, but it was very complicated. In a sense, it was very hard to understand, and also the algorithm was pretty involved. So then you can, maybe I will not write it, but years later there was an improvement by Kosaraju, and 10 years later or 11 years later there was another improvement by Lambert. Improvement meaning they tried to phrase the same algorithm in a bit nicer way. So then, based on names Kosaraju, Lambert, Meyer, this algorithm, or this kind of family of algorithms, is called KLM decomposition. So how, I will not go into that. This is really involved, and I always have to recall for myself the details. And it's, I never can memorize it. Maybe now I can reconstruct it from scratch, but it will take some time. And then, I'm just showing you milestones, so just complexity results. So then for many years, there was no real progress on it. People were trying, there were some tries. I think there was one paper on stock, which proved, I think, double exponential, that reachability is in double exponential space, but then it was proven incorrect, I think after publication or something like that. But I want to tell you one more result. 2015 from them et al. Then they have shown that reachability for two-dimensional buses. This is how I denote dimension 2. So you have two counters. Is p-space complete? And this is, I mention it because this is I think relevant with respect to the rest of my talk. So for and how they did it, they have proven that if there is a path from S to T, then there is a path of length at most exponential. So the same kind of approach. But of course, the point is how to prove. So we know this for dimension 2. For dimension 1 also things are known. And I think at around this point, it was still unclear. So the gap was in between decidability and X-space hardness. Yes, and people were thinking on it, I think. And so then Jerome Leroux is a man who did a lot of progress on buses, and together with Sylvain Schmitz. In 2015, they have proven first upper bound on complexity, which was cubic Ackermann complexity. So you may not know what is cubic Ackermann. I will give you intuition in a moment. And then the same guys, and how did they do this? They just looked into this algorithm of KLM decompositions and they analyzed it. And then 4 years later, they have proven that this that actually a modified version of this KLM decomposition is actually in Ackermann. So what is Ackermann? Do you know? I will recall. So I think that the way to define Ackermann class, complexity class, the best way is via some functions fi. So roughly speaking, this is very, very long. So I like the following. You define function fi, family of fast growing functions. The first one is not very fast growing. This is just doubling, takes n outputs to n. And then if you have fk, you can define fk plus 1. How it's defined? It's just fk composed many times, composed exactly n times, and applied to 1. Just to visualize what is this. So what is F2? you compose n times doubling, and you apply it to 1. So you take 1 and you double it n times. So this is 2 power n. Yeah? So what is f3 of n? You take 1 and apply this function, exponentiation, n times to it. So this is like, this is 2 power 2 power 2 power 2 n times. Yeah? This is also called tower function, tower of exponentials. So you can see already this grows very fast, and then f4, this is crazy, yes. And what is Ackermann? Ackermann, I will write ACK of n. This is like function fn applied to value n. So for bigger values, you apply the faster functions. Although already f3 of 3 is big, f4 of 4 is very big, and so on. Yeah. So this is Ackermann. Some people also call it f omega function, because you can see this is a limit of this function set. And then what is cubic Ackermann? This is f omega cube. Yeah, so this cubic Ackermann is f omega cube, whatever it is. So this is even more exact. And okay, so I defined two functions. I didn't tell anything about complexity classes, but based on these functions, you can define complexity classes, which are roughly speaking, set of problems which can be solved in such time, let's say in tower time, but made a bit round, made a bit robust. I mean, you don't care whether you can solve it in tower of height n or tower of height n square, or maybe tower of height even exponential. So here we don't care whether this is time or space, because solving something in time, in space, tower of n means you can solve it in time tower n plus 1, but this is the same class. So based on this, you can define complexity classes. Yeah, so now you see. And I think that, so there was a kind of maybe a conjecture that, well, maybe actually the, I think maybe going too slow. Oh, no, it's not bad. You might, yeah, so I think there was maybe a conjecture that you can, so actually reachability problem is also exponential space complete, but we are somehow as a community, we don't know yet tools to prove that it's mixed space. And I think that the feeling was, well, maybe the same theorem is true, but if you have a source and you have a target, and there is a path from source to target, there is also a double exponential length path from source to target. And if you would have such a theorem, then you would have exponential space completeness. But to our surprise, we have proven in 2019 also that this is not true. So that was me, that was Sławek Lasota from Warsaw. He spoke on this seminar a few months ago about similar stuff, but I decided this is not a problem. I think listening 2 times about something is even better, because you have to connect something. Ranko Lazic, Jérôme Leroux, the same Jérôme, and Filip Mazowiecki. So we were somehow also surprised that we managed to, first of all, build examples of vases which have very long runs, which from source to target, you have a run, but you only have very long runs. But this is intuition, yeah? You also have to prove somehow hardness. Having only long runs, this doesn't, it's not so hard. Yeah, so we have proven tower hardness. We have proven tower hardness, so F3 hardness. Maybe if you say, who cares, a Hermann or tower, these are all both huge. But if you look on this, it's between F3 and F omega, you start understanding that there is some fundamental difference. Yes? And then recently we managed to close the gap. So there in two groups independently. Jerome was working on this. And independently, me with Łukasz Orlikowski from Warsaw. So this was last year. We have proven Ackermann hardness of this of the problem. Yeah? So now we know it's Ackermann complete. Yeah. Okay. So this was to give you a story, and I hope also some kind of feeling of techniques. I think I should actually tell you a bit more what kind of a theorem we have proven, because this will give you a feeling. So actually our theorem, now I'm talking about our theorem of Łukasz, was the following. The reachability problem for 6K dimensional vases is FKR. Okay, these are vases with in dimension 6K, and this FK is complexity class based on this fast growing function. Yes, so this is not the best. I mean, you can have and then this implies Ackermann hardness, because for each K you have FK hardness, and then so this may be a shame, but I'm not really into that how this exactly implies Ackermann hardness, but it's at least you know that it's FK hard for each K. I think this probably implies that is Ackermann hard. Yeah, but just yeah. So this was our theorem, and there are better bounds on this dimension. So, like Sławek Lasota gave 3K plus 2 bound. Then the best bound by Jérôme Leroux currently is 2K plus 4. And it's known that you cannot go below K plus something. So the current open question is, can you get FK hardness in dimension K plus constant? Just like a side remark. Okay, but so now I would like to convince you, because you may say, okay, the problem is closed somehow.
So why can't you get or K half?
Yeah. Okay. Here in this result, Jérôme Leroux and Sylvain Schmitz, they actually have proven that in dimension K, for K dimensional vases, you can solve them in Fk plus 4.
Oh, okay.
Okay. So therefore, you will not go. So it means that K minus 4 dimensional vases can be solved in Fk.
Yes.
So you cannot go below K minus 4. And so currently, like open is, we are in between K minus 4 and 2K plus 4. Yeah? So what is the right dimension? And so now I would like to convince you that this is not the end of the story. And my feeling is that we are, on the way, not at the end of the way, with understanding combinatorics of vases. This particular problem is finished. But I will give you 3 examples of that, which I think they are a bit striking. For 2-dimensional vases, as I told you there, we know the problem is p-space complete. What for 3-dimensional vases? This is still, three-dimensional space. So we, in this room, yes, we somehow feel this. Of course, p-space completeness of 2 dimensions implies p-space. So p-space hardness. We get p-space hardness, dimension 3. But what is the best known upper bound? Best known upper bound is F7. So I'm much above tower. So we don't even know. Maybe the same fact is true that for in dimension 3, if from source to target you have a path, then you always have a path of length exponential. But maybe this is not even true for for tower. And this is, I think this is very simple fundamental problem.
I have a question.
Yeah?
If you have a positive result that you have a Ackermann complexity, does it also go along the lines that if you have a path, then you have a kind of Ackermann path, or is it a completely different logic?
You are talking about lower bound or upper bound?
I think it's above upper bound here. If there is a path,
no. So this is no. They look at this Karen decomposition. They decompose it somehow, and this fact about Ackermann long path. This is a consequence of this result,
yes.
But this is not the way of solving this. You have some structural understanding and decomposing somehow vast into simpler and simpler. So I think here you see that we lack understanding. Dimension 3 is not so much. Another problem is fixed vast. So in the reachability problem, your input is vast, source, and target. But in fixed, you can fix the vast, and your input can be source and target. And you can ask, what is the complexity of this problem? Of course, it depends on the vast. For some vases, it's trivial. Let's say you may travel in all the directions. But for some vases, may be hard. And we looked at this problem at the beginning. We were thinking, well, probably our techniques from Ackermann hardness can apply, and also it can be, I don't know, FK hard for any K. But currently, we think we have a conjecture that for every fixed vase, if you have source and target, there is always a path from source to target of size linear with respect to size of source plus size of target. Of course, this constant can be huge and should depend on vase. Yeah, should I repeat this conjecture?
So linear, what is the size then of the input?
Yeah, so my conjecture is that from source to target, you have if there is a path, then there is a path of length, size of S plus size of T times what is size, let's say, the biggest counter in S. Yeah, the highest value or sum of values in S. Let's say, plus sum of values in T times some constant which depend on vase. And definitely, if this would be true, this constant should depend on, in some huge way on vase. So this is a gap in between, let's say, I don't know, p-space or even linear space. Because if the conjecture is true, this is in p-space, yeah? And you can say Ackermann, up to Ackermann. Okay. So you see, it's not easy to work on it. And another thing I want to mention is extensions. So one very natural extension of this is, so here you have automaton with counters. You can ask, what if you have counters and push down? Of course, if you have two push downs, automaton with two push downs is already undecided. But what if you have one push down and many counters?
So what is a push down?
Stack.
Oh, okay.
It's a stack.
Okay.
So I hope you know that automaton with two stacks by 2 stacks, you can simulate Turing machine.
Yeah.
Yeah, so reachability in automaton with 2 stacks, this is undecidable very easily. But push down reachability in push down automaton, this is definitely decidable. But automaton with push down reachability in push down automaton and a bunch of counters, it's not clear. Conjecture is that it's decidable, but it's not even known for automaton with 1 push down and 1 counter. So it's, I mean, things are very weird here. There are also another extensions like branching buses, data buses. I mean, I will not go into details. And in all these cases, decidability is conjectured and not known. And I hope you see that automaton with a push down and a counter, this is a very, very basic theoretical model. Yes. So we are not at the end of our way. Yeah. So this is about the introduction. And now I want to give you some feeling of combinatorics. So okay, let's keep this one. I will build on top of this example. I will create more sophisticated examples. So my goal is now to show you VASes which have finite reachability set. So VAS and some initial configuration. That the reachability set will be finite but huge. And I hope, yeah, so maybe you should remember this, yeah? Can I erase it or better to keep it?
You can erase it.
Okay. There was a 3-dimensional example. I will now build a 4-dimensional example with reachability set being finite but of size tower. So let's first do almost the same as above. I will just copy the same thing. And I will add 4th counter, but at the moment nothing happens on this 4th counter. So all these 4 transitions have 0 on this 4th counter. So this is 0, 0, minus 1, 0. Here I have 4 zeros. I will not draw anything here. And here I have minus 1, 1, 0. And now I add one state R. Maybe a bit lower. Higher. State R. And in this state, you have an option of moving stuff from 1st counter to a 3rd counter. Minus 1, 0, 1, 0. So you move things from 1st to 3rd. Yeah? And then you can go here. And here you have 1. Yeah. 1, 0, 0, minus 1. So this transition is the only one which touches the 4th counter, and it just decreases by 1. I hope you can kind of see the pattern. It will just, starting from n, we will have exactly n options of use this transition. So let's now see what can happen here. So let's first.
If I was trying to generalize from this one to this one, I would do the same, but this 1 in the last transition, you have 1, 0, 0, minus 1 on your new board. Sure. I would do 0, 0, 0, minus 1. I wouldn't put this. Yes,
one. Yeah. I with 0 it would also work, I guess. Okay. But with 1 it's more elegant numbers appear.
Okay.
So let's have a look first. So what happens if we have 1, 0, K, and some L? We start in P. So as before, you can go into 2 power K, 0, 0, and N. You just repeat the behavior of, this previous guy. From 1, 0, K, you go to 2 power K, 0, 0. Now you are there, you go to Q, and you go to R. So I will draw it to just go directly to R. And in R, you move the whole 2 power K to the third counter. So you can kind of see, so you multiply, you doubled it K times, and now you will be able to double it 2 power K times. And now you go back to P. So you go back to P, 1, 0, 2 power K, and M minus 1. So I hope you see what happens. So you have exponentiated the third counter, and to pay, you decrease the last counter by 1. So I hope you will already see that if you start from 1, 0, 1, M, you can get to 1, 0, tower of M, 0. Yeah, you can apply, you do it M times. Yeah? And this is very easy. Why tower? Because this is F3. You just composed K times multiplication, exponentiation. So you can add one more dimension, generalize this a bit, and you can get F4. Maybe I should say a bit why the reachability set from this is finite. Well, so you can see that this transition can be only finite times. So after some time, you cannot use this. Here you cannot stay forever. And if you go here, you also cannot stay forever. So, and it was known since a long time that you can do this kind of stuff. But you already see why Ackermann appears here. You can get reachability up to Ackermann size. But it doesn't mean that you have the hardness for reachability. So this is the main point. Here, from 1, 0, 1, M, you can go to 1, 0, power 0, but you can also get to 1, 0, 1, 0, just ignoring all the stuff and just going all the time here. Yeah? Nothing forces you to use fully these loops, to do this double, do overwhelm. You can just go directly to nothing. So we need, so maybe I should say it like this. Let's say we want to prove this theorem. This theorem, yeah? But for some dimensional buses, you are FK high. So definitely you don't have a theorem like this, that if there is a path from source to target, then there is always a path of length, let's say FK minus 1. Because if you would have something like that, you would design an algorithm which explores all such short paths, and you would go below FK. So definitely you should have examples in which there is a path from source to target, but there is a path of length at least FK. So I will try to show you techniques in which can be used to force such a bus to take, a long path. The intuition is that having very long path and being hard is very close to each other. Right? There is no formal connection, but it's intuitively close. Okay, so now My plan is to give you 3 techniques, if I will have time. But still, I have 40 minutes, so there is a big hope. I will manage. And you can think that these are tricks on counters. So maybe, I don't know, you can reuse them on in some other places. I think that all the stuff we do is somehow very by hand. It's maybe unfortunate we don't use any deep mathematics, but maybe we create some mathematics. Yeah. Okay, so maybe so first technique will be telescope equations. Was original technique and first version of tower hardness paper was based on that, but then we managed to eliminate it. So, but I think it's still interesting. And maybe for dimension 3 it can be useful, or maybe for other cases. I will first introduce you some kind of notation. So usually we draw automata like that or buses, but it's very convenient. So how do you think about bus often? You first do something, then you do something, then you do something. So it's a bit like a program. First in a loop you do this, then in a loop you do this, then in a loop you do this. And other convenient notation for some kind of buses are loop programs. And I will define you an example. I hope this will be clear. So let's imagine you have such an example, which appears in our consideration a lot. So first you move stuff from first to second counter, and then you move it back, and you multiply by it. Yeah, and then you do something. Before you do something, later you do something. So what we call loop programs, but you can define it heavily. You introduce some new model, something like that. But I just think this is another way of illustrating buses, another way of defining buses. So first in a loop, let's say you have 2 counters, x and y. First in a loop, you decrease your counter x and you increase your counter y, and then in a loop you increase your counter x by 2 and decrease your counter y. So correspondence is obvious, and I will use this kind of definitions often. You also can define this kind of stuff by loop programs, but I think here it's easier to see what happens if you have visual drawing. Okay, so now my goal, I will show these techniques on examples. So my goal is to create a 3-dimensional vase with shortest run being exponential. Okay, with shortest run being exponential. But here I would have to, I left space, so maybe noticed. I will say unary, because what matters is how you encode numbers on transitions. Whether you encode them in binary or whether you encode them in unary. If you allow yourself to encoding numbers on transition unary, then if you add, you first add 2 power n, you go to other state and you decrease it 1 by 1, and you say from P0 I have to reach Q0. The shortest run is exponential, of course, trivially. So in order for this to be non-trivial, you need unary. Yeah. And for 2-dimensional vases, which are unary, it's known that always shortest run, if there exists one, then shortest one is polynomial. So then this is something non-trivial for 3-dimensional. The thing which I was talking there about 2-dimensional buses having exponential runs, it was all about binary. Yeah, so, okay, so that's my goal. So my trick will be, I will use the following telescope equation. So what I will write a program. Here, I will write a mass, and I will then argue that indeed the shortest run is exponential, and somehow you are forced to use your loops fully. So we have 3 counters, x, y, and z. Okay. First, you increase. Yeah. I assume that I start from all the counters being 0, and I have to end with all the counters being 0 as well. You should think that you start in some initial state, and each line somehow moves you to another state or something like that. So the reachability problem for this illustration is, can I start from zeros and end in zeros? So I first increase x and y by 1, and then in a loop I increase, maybe I should try x plus plus y plus plus. So what's the point? So here, after this this line, counter valuation is like some n and 0, and n is guessed. And I will later show you that n has to be exponential if you have to succeed. Then maybe, okay, so here I will write for I equals k down to 2. I will first write it and then comment, okay? Loop y minus z plus the loop So first of all, here you have some for loop. What is this? This is just a macro. So k is fixed, and I should actually, what I should write is I should copy this block of code, k minus 1 times. But this is just a convenient way of writing this. So you should think k, k is fixed. And then for each I, starting from k then to 2, I have the following. So maybe I should let's analyze what happens here. And yeah, so maybe let's start from the end. So let's assume that we want to reach 0, 0, 0. Yes. So here. So observe that in this block, x is not touched. Only y and z, they do some work. So after this block, x has to be the same as was here, so some n. So it has to be n. And then if z has to be 0 because it's not touched here. And here y decreases by 1, x decreases by 1, and y is decreased by k. So in order to reach 0, it has to be exactly n times k. Agree? In order to have a successful run. So what happens here? You can see that this is our well-known scenario. We first move stuff from y to z, and then we move stuff from z to y back. But we somehow divide by a minus 1 and multiply by I. So actually what we do here is we multiply by I divided by I minus 1. Weakly multiply. Yeah. So what you start doing here is, yeah, so you try to multiply the counter y first by what? By k divided by k minus 1. Yeah. Then by k minus 1 divided by k minus 2. And so on and so on. And at the end by what? By 2 divided by 1. And you can see that if you haven't moved the stuff fully from one side to the other, you will get something less. Because, for example, if at some moment you decided not to multiply, all these numbers are positive. So you should, in order to get the biggest number at the end, you have to shift all the stuff and all the stuff. Are you convinced? So you start from n and you want to achieve this. So in order to start from n, you want to achieve k, nk. So in order to really have a run, which reaches the nk 0.
So now you argue that about the shortest path to reach it.
Yes. Now I want to argue. Yeah, I'm mixing. Now I want to argue that the shortest path of this path from 0, 0, 0 to 0, 0, 0 is actual of exponential length. And I am looking at structural, I first observe how it has to look like. Yeah. So it has to have n 0 here, and k 0 here. And actually, all these loops have to be full. Yeah. Maybe we should, maybe we can spend a while. Yeah. So definitely, because you may think, okay, maybe it makes sense to move a bit of stuff here, but not move it back, and in the next round somehow cheat. So what if you don't use this? Yeah, I mean, it doesn't make sense not to fully use this loop, because each time you move stuff and move it back, it grows. Yeah, never mind whether you start like that or you start like that. Always.
So I mean, using it, you increase faster the second coordinate. Yes. So the only way of, I guess, one possibility would be that in order to get, you're just arguing about the lower bound for the path. Okay. So
yes.
So then, yeah, I mean, maybe there are other ways, but you would argue that every other way have to get at least so long here to concentrate the value at the
actually, if you don't move fully the stuff, you will not get nk here.
Just okay.
Just because if you move the stuff all the time, you have exactly this, and if you don't move something,
Okay.
you lose. And therefore, you can observe that. So what happens after first phase if you really move the stuff fully? So then you have on second counter you have n times k divided by k minus 1 after first.
Yes.
Then after second, what do you have? You have n times k divided by k minus 1 times k minus 1 divided by k minus 2, which is exactly nk divided by k minus 2. And of course, this number has to be integer, and this number as well has to be an integer. Yeah? So nk has to be divisible by k minus 1, and also by k minus 2, and also by k minus 3, k minus 4, and so on. So nk has to be divisible by lowest common multiplier of all the numbers up to k minus 1. So you lowest common multiplier, you probably know, is exponential nk. Well, these are technical details. So, but you can see, yeah. So we have some way of forcing things to be exact. So this is like first way, but this looks somehow very ad hoc. Yeah. So let's look at the next technique. So the more, let's say, systematic approach to this would be to say,
So single exponential is best known for 3 plus?
yes.
Wow.
This is weird. So, yeah, I guess you know that if you have two-dimensional automaton with two counters, but you have 0 tests on these counters, then the reachability problem is undecided. I'm not sure, is it known or not?
Say it again, please.
If you have two counter automaton, so it's exactly like two VAS, but you have 0 tests, then it is undecidable. Reachability problem is undecidable. It's called Minsky machine as well. How you prove it? It's rather easy. You take automaton with 2 pushdowns. You can simulate pushdown by 2 counters because you can think that you can simulate it in binary, and then from automaton in 2 pushdowns you can show that automaton. I'm just sketching anyway. You can show that automaton with 4 counters and 0 tests is undecidable, and then you can decrease number of counters. But this is like a well-known fact in automata theory that automata with 2 counters and 0 tests, they have undecidable reachability.
Did you say that you can simulate the stack with 2?
You can simulate a stack with 2 counters because let's say if you
do the 0 test as well.
Because you have 0 tests.
Yes, exactly. Okay. Yes.
So if you have let's say 10 different, let's say you have stack with 10 different stack letters. So if you have 7 for 3, you can think that this is a number, 347, and if you pop, you go to number 34. So you have to be able to divide by 7. Roughly speaking, yes, divide by 10. Divide by 10. If you have 10 letters, then you treat this as in base 10. So how to divide by 10? If you have on one counter you have 347, and on another you have auxiliary counter, you already saw this trick. You move the stuff here, and then you move it back by subtracting 10 here and adding 1 here. And if you have 0 tests, you can check whether you fully did it. So this is why how you simulate pushdown by 2 counters. And then you can say, okay, if I have 2 pushdowns, I can have the same auxiliary counter actually. So from 2 pushdowns, I can go into automaton with 3 counters and 0 tests, and then you can get rid of the third counter. Let's not go into this. But
what is the undecidability proofs for the 2 pushdowns?
how it works?
Yeah. I mean, you have a reachability problem for Turing machine.
Okay. This is a halting problem. So this is undecidable.
Yes.
And if you have a Turing machine and you have a head here, you think about this as 2 pushdowns. Such pushdown, which has top of the stack here,
yes,
and such. So here is top. And if you move head left, you pop here, you push here.
Nice.
There are some details, but
Nice.
this is very easy. I can tell you how to simulate 2 counters by 3 counters. I think this is very nice. If you have 3 counters, let's say X, Y, Z, now you encode this as new counter 2 power X, 3 power Y, 5 power Z, and you have auxiliary counter. And now in order to increment this, how do you simulate incrementing this by 1? You have to multiply this by 2. But you move stuff here, and you move it back by divide. And the same, 3 and 5. So this is how you get, So if you have 2-dimensional vase and 0 tests, you are undecided. You cannot hope for simulating 0 tests. But anyway, somehow more robust approach to forcing runs, to be exact, is to simulate some bounded number of 0 tests by vases. You can think that if you have reachability problem, you ask, can I reach target from source? You have some very small amount of test, because at the end of a run, you test whether you are in the target configuration. Let's say target configuration 0, 0, 0, 0. I haven't told you, but you can assume for free that your source configuration is some state and 0 values, and target is some another state and 0 values. Because if it's different, in the last step you just remove all this. Okay? So you can think at the end of the run, I have 0 tests on each counter. And our techniques somehow boost this very small amount of 0 tests to more. We can, by testing at the end of a run till counters for 0, we show how to simulate more 0 tests during the run. So that's the high level intuition. So now I will show you our technique of controlling counter. Counter, we invented it in this paper of Ackermann hardness, and because this was a tool to prove Ackermann hardness. We also used another tool which was in tower hardness. And but this is also useful for some. So recently we work on low-dimensional vases. As you see, this is striking, but we don't understand how 3-dimensional vases behave and some other. And I think there were maybe some fundamental things hiding there. So I think it's worth to go there. And so we work on this. And this controlling counter technique is also useful for this low dimension. So first I will just show you some illustrations. So imagine you have some run and you have some counter X. I think this will be the last technique which I show you, but it's let's say you have some counter X, and let's say that your run is like that. Starts in some configuration C0, then in some configuration C1, you want to check whether counter X is 0. Then in some configuration C2, and then in some configuration C3, and then you proceed. So in 3 moments along your run, you want to test your counter X for being 0. Usually you can do it just once at the end of a run. But I would like to show you how to simulate 3 0 tests, and then you will see that you can do more than 3. And let's say for simplicity that our counter X has value 0 at the beginning of the run. And let's say that here we have, it has some value x1, here some value x2, and here some value x3. Okay. So it's of course enough to check whether sum of these three values is equal 0. Because you know they are non-negative, so it's enough to check whether this is 0. So natural solution would be to add to your system one new counter, which keeps some of these three numbers. Somehow, you know, you can think, yeah, I add to my system some additional counter, and here I just somehow move this value to my counter, then here as well and here as well. But you already feel that VASs cannot do something like that, like move counter value of this counter to another counter value. Because you can do this somehow transfer like this loop, -1 here, +1 here, but you are never assured you will do it fully. Problems appear, yeah? So how you do this? And this is the trick. So assume that effect of this run on counter X is Y1. Effect of this run on counter X is, let's say, Y2, and this is Y3. And so what we have is actually X1 is Y1, X2 is Y1 plus Y2, and X3 is Y1 plus Y2 plus Y3.
So these
Y's,
these positions where you want to control the counter, are they some states, fixed states in your automata?
Let's say they are some states.
So the first time you reach the state, this is the time you want to test.
Let's say I'm doing this a bit that hand way, but you can imagine it like that.
Okay.
Yeah, so we actually have to check whether this sum is equal to 0. So now I'm telling you how you can actually keep in some additional counter, which will be called controlling counter, this value. So what you have to check is whether this plus this plus this is 0. So whether you have to keep 3y1 plus 2y2 plus y3 in this controlling counter. How do you do this? In the first part, you just simulate this counter, but you multiply it by 3. So for whatever happens on counter X, so you add this additional controlling counter C, and if X is incremented, maybe it's, let's say this controlling counter is what? Z. Increase it by 3. Why by 3? Because still somehow 3 0 tests are waiting for us. If you go here, let's say this is some other state, then you can apply different transitions. Then here you simulate each increase or decrease with multiplied by 2, and here by 1. And at the end of the day, you have on your counter this one. So you can check this controlling counter for being 0 at the end of the run, and then you are assured that X1 was 0 here, here, and here. Which is very nice, because usually what you would do is you would keep, 3 copies of your counter, and just after this time, maybe I should say it before. What you can do is you can add 3 additional counters, and first copy would stop doing anything after this place, second copy after this place, third copy after this place. But here now we can do it just with 1. And of course, you see there is nothing special about 3. You can do it also for 7 0 tests. You can also do this for linear number of 0 tests, let's say. You just, for each 0 test, you have to have additional state in which you change, how the transition behaves, how the controlling counter simulates the important counter. And what is also important is that controlling counter can control not only one counter, but it can control many counters. It can be that you have counter X, Y, and Z, and you have controlling counter C. And if counter X increases and counter Y decreases and counter Z does something else, then on C you keep total. If because of X C should be increased by 5, and because of Y, C should be decreased by 7, you decrease C by 2. You just, because at the end of the day, the controlling counter will just keep some of values of counters in, in relevant moments. So that's the trick.
Then the controlling the counter eventually it means that you that if it's 0, then on some your auxiliary counter you get a 0 after doing the whole.
Yes. So if all the places where I want my counters to be 0 are 0, then my controlling counter is 0, and maybe even more importantly, if and only if. So if I check that my controlling counter is 0 at the end of a run, okay, the controlling counter keeps exactly some of the values in the controlled moments.
Okay, that's true. Yeah.
Let's say it like that. And the last thing, maybe one comment. So I was planning maybe if we go fast, but I think we go anyway, not slow, to show you one more technique, which would be like multiplication triples, but I think that, so I wanted to show you more directly from which problem we reduced to show FD hardness. But yeah, I don't know, I'm thinking whether I should comment something on it, but maybe not. It's another technique to simulate 0 tests. And maybe I should, before showing you some example of this, I will just maybe comment very briefly that in general, like it's known that the following problem is FD hard. Okay, so I told you that automaton with 2 counters with 0 tests has undecidable reachability. But now if you say, I have automaton with 2 counters with 0 tests, and I ask not does it have a run, but does it have a run which is such that counters don't go above some threshold, and this threshold is let's say FD, then you can see that this is of course decidable because the space of all the configurations is like FD squared times number of states. So this can be done in FD, and this is actually known to be FD hard as well, for D at least 3 or something like that. So you reduce from this problem. You are given an automaton with 0 tests and with 2 counters, and you ask, does it have a run with such that counters don't go too big? And then we show that VASs can simulate such things. So if your counters are bounded, then you can simulate 0 tests. And general, this is very hand wavy, but what we showed that is if you have a triple in your VAS of a form B, C, and B times C, then you can simulate B-bounded counters. So this is maybe not very weird, because if you have X, and for X you add B minus X, and let's say you start from Z, you have a B. If your counter has value 0, using this you can keep. Let's say you start from X being 0 and X prime being B. So you can see that by keeping X plus X prime always to be equal to B, you can force that to consider only such runs in which X don't go above B. Okay? But if you have such a triple, you can simulate C half 0 tests. And this is like interesting fact, which I don't know, maybe I can explain a quarter or something like that. And the whole challenge was to produce a VAS gadget which can produce something like that, such a triple. FD of N, then some C, which is guessed, and then some FD of n times C. And by what I told you is that if we have a gadget which produces something like that, then you can simulate FD bounded runs of to counter automata with 0 tests. So that was the point. So our main trick was to produce such triples. And we produced such triples from smaller triples, somehow inductively. If you have a gadget which, maybe let's stop on this level of details. So maybe you can observe that producing something like that for small numbers is very easy. So if B is small, how you can produce this?
So another question, can you reduce from the hardness, from the problem of reachability, where you cannot go too high?
Yes, so I'm asking, let's say I have an automaton which can go too high, but I ask, does it have a run which doesn't go too high?
But it's still on the truncated grid, so you don't go below 0.
Yes.
And then, and what is the proof of hardness there? Is it like principled, or is it?
It's the same proof which I, essentially the same proof which I told you about undecidability, but you say you can start from Turing machine which has FD bounded space. And this is known to be FD complete, and then everything proceeds. So how to produce something like that if B is small? You just first, add B 0, 0, and then in a loop, you add 0, 1, B. And if a loop, iterates C times, then you produce this. Okay. So the trick is to get such triples for big B. Okay, so this is maybe what I wanted to tell you at the last part, but I didn't have time to go into details. And so I don't have time, so I will not show you example of this controlling counter, but I hope you saw the point, I mean, you just add one counter and you check it for 0 at the end. So my point was to, let's say, to look into similar example as here and to show that adding one counter, you can compute, let's say, 2 power n. Okay, I think this is it. Thank you very much.